In this video, we will show you how to implement a complete engine and tire Tire SFX system. But before we dive into the technical details, let's look at the final results. You can download the demo in the description below. Its size is around 1 GB, mostly due to textures and mesh files. The plugin itself is only several megabytes. In the last 4 months, we have made various improvements and breakthroughs to our procedural SFX framework. There are a lot of new and exciting things we want to share with you. Today we will focus mostly on the vehicle sound system. This tutorial will be a bit long because we want to make it self-contained, so you don't have to watch other videos to understand it. To make it easier to follow, we divided it into several parts. They are marked with the timestamp shown in the description. You don't need to watch the whole video or have to understand everything we discuss here, especially the parts about the details of each graph. Feel free to skip them and jump to the quick review or blueprint parts, where we show you how to set up and update the graphs at runtime. Let's jump right into the car engine graph, because we want you to be able to create your unique vehicle sound. This graph has a lot of exposed input parameters. To adjust them, you will need to have a brief understanding of what they do. So let's examine this base graph more deeply. I will try to explain everything as briefly as possible. If you have any questions, feel free to contact us on Discord or in the comments below. The first and most important part is the harmonic layer. It outputs both audio and the base frequency, F0, of the current RPM. The base frequency is critical for other layers to work correctly. Number of pulses per revolution is calculated based on your engine's number of cylinders. For cars, it's half of the total cylinders. RPM and throttle are updated from the blueprint at runtime based on the player's input. Idle RPM should be the same as the one in your chaos wheel component. You can keep it at 800 RPM for cars. RPM variation noise factor, random period, F0 fluctuation, min and max gain random % add noises to the base frequency in its harmonics. These are important for simulating a real combustion engine, because these values don't need to be adjusted for each type of vehicle. We don't expose them as graph inputs. The next 3 inputs are new and they are extremely important, because they will affect how RPM is converted to F0. In the old version, we used a simple linear equation. While theoretically correct, this made the graph entirely dependent on input RPM. Thus, you needed to connect it to a good engine framework to simulate realistic RPM slopes. This made sound previews difficult within the graph itself. Sometimes you just want to simulate simple engine sounds without a full framework, like for chainsaws or passing aircraft. In this version, we've added an equation that simulates realistic RPM slopes within the node. When enabled, the node assumes your RPM curve is linear. It will convert the input RPM to F0 using the new equation. The equation and its parameters come from real recordings of cars accelerating from idle to 6,000 RPM. Let's compare the differences when toggling this feature. I'll set the target RPM to 6,000 and play it. Now I'll disable it and play again. A real RPM slope follows a lope curve after passing the optimal RPM and approaching the max RPM. Unfortunately, Chaos Wheel Vehicle component uses a sine curve which isn't good enough to simulate the RPM curve of real vehicles. So keep this enabled unless you have a good engine framework. Now, F0 min is the base frequency at the idle RPM. Previously, we automatically calculated this from the idle RPM. But testing on various vehicles, cars, jet boats, planes showed that separating these produces more unique sounds. Two vehicles can have the same idle RPM but have a different F0. RPM to frequency slope affects F0 when RPM exceeds the idle RPM. For example, at the idle RPM it's around 25 Hz, which is F0 min. If I raise RPM to 6,000, it's 66 Hz. Now, if I change this to 2, it's 122 Hz. Back to idle RPM, it's 25 Hz again, that's the F0 min. Number of modal deceleration determines the number of simulated harmonics when the user releases the throttle input. A harmonic modal refers to the model files bundled with the plugin. Currently, we provide 10 models for 4 categories of cars, 1 jet boat model, and 1 plane model. This may seem limited, but with all the adjustable parameters, you can create countless unique engine sounds. I'll demonstrate this later. Number of harmonic modal sets to maximum simulated harmonics. -1 means we use all data from the model file. Note that in the model file, the base frequency is at index 0. Its harmonics are sorted from low to high frequencies, so you can reduce this parameter to reduce high-frequency harmonics. Frequency scale applies a multiplier to all frequencies. It's mainly used to simulate the Doppler effect. The built-in low-pass filter isn't used here because we have a low-pass filter at the output. Okay, next is the overtone layer. A car graph has 2 models, one to capture the engine sound, aka the harmonics we've just discussed. The overtone layer captures all the things that vibrate and contribute to the unique sound of each car, such as the frame, exhaust pipe, fans, etc. The output of this node is multiplied by the harmonics to create the final overtone. This method efficiently simulates different vehicles without heavy performance costs. There are only 2 parameters here, the overtone model file, and this frequency scale allows you to create different variations from the same model. Now, intake and exhaust are crucial states in combustion engines. All engine sounds are created thanks to these 2 operations. 4-strokes engines have additional states, but we can ignore them here. 2-state force synth node is used to simulate the intake and exhaust force of all cylinders. The first state is the intake part, and the second state is the exhaust part. Downscale and rise scale are chosen based on a physical equation. You don't usually change these 2. You mostly change the frequency scale and the duty cycle to modify the rumbling sound of the engine. The output of this node is then multiplied by the harmonic, the overtone, and white noise. This white noise node is used to simulate fan operation. Engine sounds originate inside the car and exit through the exhaust pipe. To simulate this, all layers are passed through a delay node, then into an early reverb node. The results are then mixed with the harmonic and overtone before passing through a low-pass filter. Here, we use one of the new reverb nodes, called early reverb. I will talk more about the new reverb system in the next video. This node is much simpler than the old reverb node. It also runs faster and is more realistic. We use it to simulate both the reverb effect inside the car and the reverb effect of the environment. It's more efficient than doing reverb 2 times. These inputs are self-explanatory. Fmin and Fmax are the frequency ranges of the input signal. We use 10,000 Hz instead of 20,000 to save performance. For cars, this is enough. Above this, it's hardly noticeable. Frequency spread affects how we calculate the frequencies between Fmin and Fmax. Not very important, just keep it as 1 and forget about it. Decay min is the most important input of this node. It affects how long the reverb effect lasts. If you want to hear more reverb, reduce this value, otherwise increase it. Since this node can only simulate early reverb, decay min should never go below 20. Otherwise, it will create metallic artifacts. At 25 Hz, the decay rate is equal to the decay min. But the higher the frequency, the higher the decay rate will be. The decay curve scale will affect how fast we increase the decay rate for high frequencies. The fusion scale affects how airy the final result feels. And finally, the gain is the second most important parameter of early reverb. So that's the basic flow of our layers. Now, this part contains all the math we use to control the gain of different layers. These correspond to different states of the vehicles, such as idling, throttling, braking, and slowdown. Again, F0 min is the minimum allowed base frequency in the harmonic parts. As the RPM rises, F0 will also rise. When F0 is higher than or equal to F0 full, all harmonic frequencies are used, and no gain reduction will be applied to all layers. Finally, this part is used to create the throttle effect in startup. Technically, it's better to do this on your engine framework by increasing and decreasing the RPM. It will sound better, and you can sync VFX with SFX. But it's not easy to do that with Chaos Wheel component, so we add it directly inside the graph. It's easier to view these parameters in the child graph. You can disable it by setting this to false. If enabled, on startup, the engine will sweep from the idle RPM to the target RPM. Throttle RPM per second controls the increment speed. After reaching the target RPM, the RPM will increase slowly for a short duration, which is controlled by the release delay input. Release duration is the time it takes to go back to the idle RPM. This is done to simulate a real startup throttle of a car, while it is meant to be used with a cold start graph. It is also very useful to quickly preview the sound when tuning the input parameters. By the way, the graph for the cold start effect is this one. The control logic is very complicated because we need to simulate the entire startup mechanics. We don't have time to go into details. The only thing you need to care about is this input. This duration should match with this duration, so when you play two graphs at the same time, the timing is correct. I will explain the reason behind this in it and trigger control by floating an extra verb video. Spatialization is straightforward. If you disable HRTF, this node becomes a panner node. The panner clamp here prevents the sound from completely going silent on one channel. For example, if the sound is at 90 degrees, which is on your right ear, then the left channel has zero gain. This is common for stereo panner algorithms, even though it's not correct. Realistically, there will always be sound coming to both ears. This clamp is also scaled based on the distance to make it more realistic. Note that this input only applies to panner mode. If you enable HRTF, then this does nothing. For cars, I think HRTF is a bit overkill. Stereo panner is good enough. HRTF is more useful for aircraft. We use the enclosed factor from our interface to control the reverb. This entire graph only uses the first three parameters of our interface. Open room factor and room size are not needed for vehicles. If the enclosed factor is 0, you are driving in a totally open space environment. The gain of reverb is multiplied by 0.5 in this case, and the delay is also increased to 50 milliseconds. If it's at 1, that means the cars are surrounded by other structures, like when you are driving through a tunnel. To show this effect, let me run the demo again. Notice the sound before and after I pass through those weird structures. The enclosed factor is very useful for all kinds of sound effects. For example, the rain sound is also affected as explained in the weather video before. Now, finally, distance attenuation. When we talk about distance, we mean the sound coming from NPC cars and not the players. Distance attenuation max is the maximum distance at which the sound is barely audible. And this is the fall off of the low-pass filter before the output. So the farther the car, the lower the frequency. As well as gain reduction. Note that the dry part gain reduces faster than the reverb, because you will hear mostly reverb from distant sounds. This is very important for distance perception. Lastly, distance is also used for the Doppler effect. It's an important effect to simulate the passing by of cars. When a car runs towards you, the frequency is scaled up, and when it runs away from you, its frequency is scaled down. Okay, that's a lot of things to remember. Let's review all the important input parameters again. It's easier to follow by using the input of the child node in the members panel. They are sorted by name, while the input is sorted by our specified order. Hopefully, Epic will allow us to change this in the future. Final gain is the engine global gain. This allows you to scale the gain of the entire audio without having to adjust all layers individually. Dry gain is the gain of the harmonics and overtone layer. Reverb gain is the gain of the reverb layer. It includes harmonics, overtone, fan noise, and their multiplication with intake and exhaust force. Reverb decay scale and decay min will affect the decay rate of the reverb effect. Avoid reducing them because too much reverb will make it sound unpleasant. Reverb diffusion scale and frequency spread can be kept at the default. Now F0 full, F0 min, and the slope factor all work together. Input throttle and RPM are updated at runtime from the blueprint. F0 min is the frequency at the idle RPM. When the base frequency reaches F0 full, no gain reduction or filtering is applied to all layers. If you want the sound to feel more high speed, increase F0 min or this RPM to frequency slope factor. Then, to set F0 full, you can watch the value of F0 when the RPM is around 4000. Modal engine should use models prefixed with engine and not affixed with overtone. Harmonic gain affects the gain of the harmonic layer in both the direct and reverb layers. While overtone and exhaust layers are created by multiplying with harmonics, this does not affect them. This is the maximum number of modals that will be used. -1 means we use all. Reducing this will remove higher frequencies first due to how they are sorted in the model file. This is the number of modals to be used when the input throttle is 0 or when the car is switching gears. For cars, number of pulses per revolution is equal to half of their number of cylinders. For 2-stroke engine, used mostly in motorbikes, jetboats, or chainsaws, it's equal to their number of cylinders. Changing this will affect the RPM to base frequency curve. So you will also need to adjust F0 full as mentioned earlier. If you want to make the car feel more expensive, increase this. Modal overtone should use model files affixed with overtone. It doesn't need to match the one used in the modal engine input. The overtone frequency scale the base frequency applied to the overtone layer. The gain here applies to the overtone in the direct and reverb parts, but does not affect the exhaust layer. These two are very useful to create unique sound variations without having to adjust everything. Now we come to the exhaust part. You don't need to change these two scales. You can change the duty cycle and the frequency scale to create different variations. Though avoid changing them too aggressively, or else it will sound weird. Harmonic gain, noise gain, and overtone gain affect the mixing gain in the exhaust layer. To balance the gain of the sound when the car is idling, the exhaust idle multiplier is used. This increases the exhaust layer gain and reduces the harmonic and overtone layers gain. If you want the car to do a throttling effect on play, enable this. On startup, the input throttle is automatically set to 1. The RPM will be swept from the idle RPM to the target RPM. Then, after a short duration, specified by this release delay, the input throttle is released. This delay duration is important to simulate the free rotating period of a car engine on startup. The release duration is how fast the RPM will return to the idle RPM. And throttle RPM per second is how fast the RPM is increased over time. Okay, let's try creating a new, unique vehicle engine sound from an existing graph. First of all, I will change the overtone model first because it is easy to change and has major effect on the output. Let's use the overtone model of car 2. So the exhaust harmonic gain is 1, and the overtone is 0.5 here. Let's see what happens when I increase it to 1. Not bad, but I think we should reduce the overtone frequency scale to 0.5. Okay, sound better. Let's also increase the overtone gain in a direct path to be the same as the harmonic gain. Now, to make it sound more unique, I will change F0 min. Since we reduced the frequency of the overtone, I will increase this. You can also decrease it if you like. This is clamped at 50 Hz because meta sounds pick up on the range of the bass graph, or something. I would just set it to 60 Hz. Let's preview it again. Yeah, sound even more different now. But we won't stop here. Let's also change the curve factor. Again, you can change it up or down. If you view the S0 at the output with the target RPM at 4000, it's near 150 Hz now, so I will set this S0 full to 150 Hz. Set this back to 6000 again and preview it. Let's also do a run test. Because the preview alone does not take into account the difference in car mechanics setup, I will replace the sports car with the new graph. And it sounds different compared to both car 1 and car 2. Okay, let's set this back to sports car 1 before I forget. And remove the graph. Technically, we can create many presets from 10 models by mixing overturn and harmonic, likely up to 100. Also, do remember that we have a modal merger node to allow even greater customization. But that will pollute the plugin with a lot of variation graphs. So we believe it's best to let users create their own variations. Normal and sports car categories are good for cars with the switching gear RPM higher than 5000. This means the switching gear settings in the chaos wheel component. Sports cars are modeled and fine-tuned to have less noise than normal ones. Fans are optimized for cars to run at lower switching gear RPM, likely around 3000 to 4000. Their overtone and the exhaust force are also tuned to include their frame vibration. Trucks and vans tend to be noisy due to their size and their transported goods. You can see that we set the overtone to be very low here to reduce the noise. To make it more realistic, you can increase overtone gain, and reduce this S0 full to below S0 min, so no filtering is applied. All the gain reduction we apply is actually to make it less realistic by reducing the overall overtone and exhaust noise. If your engine framework simulates a realistic driving experience, then you can make it more realistic, but most racing games nowadays aren't. Thus we need to apply filter and adjust gain to handle fast and sudden RPM changing without making it sound weird. The final category is Formula. Currently, we only have Formula 2, but we are looking to add Formula 1 models. Initially, we want to add a graph for a tank, but the thing is, while the engine sound is very simple to model, we can even reuse models from our cars. What makes it unique is the sound from the tank tracks, which leads to problems like creating a new track graph for tanks, real play testing, and other things, which is out of scope. So we do not have a tank graph for now, but we succeeded in improving the jet boat sound with the new graph. Now they sound exactly like the recording, mostly thanks to the reverb. Jet boats just have a lot of reverb due to their low frequency. And that's all you need to know about the new engine graph. Next, I will show you how to set up and use this graph with the Chaos Wheels component. In the blueprint folder of the plugin, you can see a file named Vehicle Engine Control Example. In this file, we show you how to update the RPM and input throttle based on a Chaos Wheel component. The logic is very simple. If the car is accelerated in the same direction of the throttle input and no brake is pressed, then this is set to 1. Otherwise, it's set to 0. The RPM is read directly from the component. Now, we will use the default vehicle template of Unreal to show you how to use this function. If you create a blueprint project from that template, Unreal will create a base blueprint class called VehiclePawn. Inside the blueprint, I added an audio component for the engine sound, and set it to use a car graph. Then, in the tick event, I simply used the update engine SFX to update the RPM and input throttle. That's all you need to do, very simple. Now let's move on to the system for the Tire SFX. The graph for it is much simpler. Currently, we support mixing between 6 different types of materials: sand, grass, gravel, dust, snow, and water. By changing the mixing ratio, you can simulate all different kinds of terrains. These 6 layers are divided into 2 categories. The first 3 are the bottom layers. Dust, snow, and water are the top layers. The top layers are those that can cover or replace the bottom layers. They are meant for dynamic changes in terrains, just like the weather effect in the demo at the start. The road can be covered by dust, water, or snow. Let's take a look inside the space graph. We don't have time to cover everything, and you must have changed again, so knowing how these layers works aren't needed. So I will only explain this concrete factor a bit because it's the unconventional one. It's used to create the skidding effect. This factor is used to control the decay rate of this node. The decay is low when it's 1, creating that continuous high-pitched sound. When this factor is reduced, the decay rate goes up, making it sound more like skidding on sand. When the decay rate is high, the loudness of the output audio is also reduced. So we increase the gain here to balance it out. This skid strength is updated based on your wheel status, which we will see later. The water layer is a special one. The layer water input is connected to the water depth of this node. If you open it, you will see it has 2 layers. One uses the burble generator to create the drop and drain effects. The other one is to create the splashing sound. What I want to point out is that the depth controls the radius of the generated bubbles. On shallow water surfaces, we will generate very small burbles, meaning mostly mid and high frequencies, to make it sound very light. In deep water area, we generate bigger burbles, which has low frequencies, to make it sound heavier. Let me demonstrate again how the tire system works before we move to the blueprint part. Notice how the tire's sound changes when the road is covered with more dust. Now, let's test with those puddles. You might need to increase the volume a bit to hear the differences. Feel how the sound changes based on the water depth, creating a better interactive experience. By the way, the puddle sound is generated by spawning this graph directly, because it won't move outside of the puddle. The water layer here is only used for rain because it moves with the wheels. They use the same graph but are controlled differently. Again, in the example blueprint, you can view our update tire terrain SFX function. Here, you can see the preset parameters for different road types. This function is just a rough example of how to do it. We want to make it easy to understand, so we make it very simple. Unlike the engine SFX, Tire SFX require much more custom setups, because it requires knowledge about the vehicle, the terrain, the wheel condition, and even the weather. Let's visit the base vehicle pawn blueprint again. We also update the Tire SFX inside the tick function. Dust, water, and snow are read from a weather system. By the way, here, we use a paid third-party plugin for weather. It's called Ultra Dynamic Sky. Note that the input audio here is an array. The car has 4 wheels, so when we can play, we spawn 4 audio components and attach them to each wheel. The car tire graph is passed in here. Okay, this function is a bit more complicated than the engine one. We will loop through each wheel and update the audio based on its current status. Remember to update the speed with the absolute value of the speed from the chaos wheel component. We read the state of each wheel from the component. Firstly, we check if the wheel touches anything. If it's in the air, then we can fade it out by using the unstop trigger. If it touches anything, we move the sound to the location of the contact point. Then we read and combine both the skidding and slipping strengths to set the tire skid strength parameter. Finally, we read the physical material to update Tire SFX. This function converts the name of the physical material to the enum used inside this function. The name of these materials must match the one inside this enum for it to work. This setup is neither flexible nor a good way to do it. But since the plugin is mainly for sound effects, we don't want to dive too deep into gameplay logic and other stuff. So this just serves as a simple example of how to update the tire graph. And that's it for Tire SFX. Before we end the video, I want to talk about how you can further improve the whole system. Firstly, the current version of Chaos Wheel component doesn't support limiter effects. Instead, it uses a simple sine curve to change the RPM from idle to the maximum RPM. Meaning when the RPM reaches the maximum RPM, it just stops increasing. In a real car, however, the RPM slope is much more complicated. When the RPM passes the maximum RPM, aka the red line, the limiter kicks in. Depending on the type of limiter, different effects will occur, but the RPM will always drop below the red line. If you continue to hold the throttle, it will eventually pass the red line and the limiter will kick in again. So the RPM slope near the red line looks like a saw wave. This whole thing creates very interesting sound effects, which you usually hear in most racing cars. Our graph does support rapid RPM changing. We also provide the backfire effect separately. So if your engine framework supports limiters, then you can use our graphs to simulate their SFX too. If you use the Chaos Wheel component, then you might need to work around or extend the code to add this effect. Though if your games just feature some light driving experience, then it will not be worth it. The plugin is mainly about sound effects, so supporting engine code and the blueprint side is out of our scope. In the future, I hope Chaos Wheel component implement a real RPM curve instead of using a sine curve. Secondly, if you want your vehicle system to sound even more unique, you will need to work on secondary effects. The impact sounds when the car hits other objects are a great place to make each car feel unique. Or playing backfire sounds when the players suddenly hit the brakes then throttle again. That will make it more interesting. Based on your car models, you can add some unique things, like the impact sound between the long exhaust pipe and the car frame. Since we expose F0, you can use it to determine the impact frequencies. For trucks, you might add impact effects based on the transported goods. When driving on terrains with many small rocks, you can add the colliding effects between those rocks and the car frame. All of these SFX can be done by using the plugin. You can look for impact graphs in the melee or ranged weapons folder and start from there. Of course, you can use your own recordings too. The next video is about the new reverb system, and in the one after that, we will introduce a new node which helps you to create even better impact sound effect. The input of the new node is audio, so it further enhances the synthesizing results from the old nodes. Bye for now, and I'll see you again soon.